Welcome to ePathshala lecture series on postgraduate courses. We are discussing on cryptography and network security. In this we are going to discuss about modes of operation. Before going to discuss about modes of operation, we need to understand the last lectures where we discussed about DES algorithm. In that, what is the key generation process? Then we are going to discuss about what are the various modes of operation, and also we are going to discuss about five modes of operation: EBC, CBC, CFB, OFB, CTR. Finally, we are going to compare the modes and to discuss about remark over them. So, in the last lecture about the data encryption standard, we have discussed about the rounds and its operation, and addition to that we have discussed about round key generator. So, now we need to know how the keys are generated. As we know earlier, there will be a 16 rounds, each round will get a 48 bit key. So, the round key generator will help to get this 48 bit key. So, how it is going to be generated? The key generation process involves 1648 sub keys from 56 bit key. So, actually we know very well the input for DES algorithm is 64 bit key, and they will be removing the 8th bit. That means the 8th bit, each and every 8th bit is dropped. So, from 64 it is changed to 56 bit key. So, that is going to be dropped, that is called as a parity bit. So, that parity, each and every 8th bit is a parity bit. After dropping the parity bit, 8th bit, we will get back 56 bit key. So, this 56 bit key is then converted back into 48 bit sub keys. That process is explained from the following. First, the key is loaded according to the PC1, that is your permutation combination 1, then it is halved, that means it is going to be divided into 2 halves. Then each half is rotated by 2 bits in every round except first, second, ninth and last round. The reason for this is makes it secure against the relatively key crypt analysis. So, what happens is they are not able to guess, even though they know some of the partial key, it is very difficult to guess the what would be the round key. Then the 48 out of 56 bit keys are chosen according to the compression permutation. So, this diagram which is explaining here, it is about key with parity bit. That means, as I mentioned earlier, this process is talking about this round key generator. What is the internal process involved in the round key generator is explained in this particular block diagram. So, here we can able to see that initially key with parity bit, that is the total size of the key used for encryption processes by the user, that is Bob and Alice want to communicate, they will share the key, that size of the key is 64 bit. After that it is entering into the parity drop. So, once it is entered the parity drop, as you know very well, every 8th bit is going to be dropped, then it is converted into 56 bit key. This 56 bit key is divided into 2 halves, one is 128 left, another 28 right. So, left half and right half, then it is entered into the shift circuit. That shift will take care of shifting them to the left 1 bit. So, the round shifting is mentioned in this particular table, where we can able to understand for first, second, 9 and 16 there will be 1 bit shift, whereas other round it is going to have 2 bit shift. So, based on this only the shift block is going to be working. So, left shift 1 bit for first round, second round it will go for 1 bit, third round it will go for the 2 shift, that is left shift. That binary values are going to be shifted to left, and then this 128 bit is entering into the compression P box as mentioned in the steps. Then it is finally compressed to both the halves, both the left and right half is entering into the compression where the total size is 56, then finally it is converted into 48 bit. So, this 48 bit is called sub key, which will be used for round 1. The similar process is going to be happening parallelly along with the encryption what we are discussing in the last class. With respect to each and every round we are going to get the sub key. So, totally there will be 16 subkeys are going to be used for encryption process. So, the parity drop is mentioned as we can able to see that each and every totally this is going to be the table how it is going to be dropping the parity bit, that is where it is the initial step. Then the next step we need to understand number of bit shift is going to be happening, that is with respect to the shift left where the block is going to be taking off, how we are going to shifting the bits. And finally, we have a compression table where it need to compress the 56 bit key into a 48 bit sub key. So, this table will be helping to. So, overall what process are involved here is for the key generation for each and every sub key generation process where we need left shift as well as the compression. So, left shift compression will be happening for each and every round, whereas parity drop is going to be happening at only first step before the key is entering into the key generator. So, this key generator will give the 16 keys which is used for the encryption process to generate the cipher text. So, that is all about the DES operation with respect to the encryption as well as the key generation. Now, we are going to discuss with the operations, modes of operation. So, normally we say cipher with respect to the modern cryptography, there are two different way of encryption, that is either a block cipher or a stream cipher. So, this is modes of operation which is explaining with respect to the block cipher encryption fixed size blocks. So, the block cipher where encrypting the input data as a fixed sized block. So, for example, DES already we know when I am taking a particular plain text may be varying in length, but for each and every encryption process it will take only 16 bit block of data with a 56 bit key. So, a neat way to use in practice given usually have an arbitrary amount of information to encrypt. So, what is happening, partial message into a separate block for ciphering. So, now as we mentioned the message length is not always going to be a 64 bit. Suppose I want to encrypt a message where meet me tomorrow at in the particular place, then if the message is sent, if the message want to send from, for example, Alice sending a message to Bob as meet me at Tahoe party, then the message is not going to be exactly 64 bit, it need to be divided into 64 bit blocks. That is what it is saying, partitioning message into separate block for ciphering. So, the modes of operation describes the process of encrypting each of this block under a single key. So, now we need to understand what is the importance of this modes of operation is. This is the process of encrypting each of this block under a single key, that is what we say as a 64 bit key, or it is after dropping it is a 56 bit key. Some modes may use randomized input values, that is we are going to discuss. So, the modes of operation taxonomy where it says modes of operation, we come out with 5 different mode of operations where we have one is electronic codebook ECB, another one is cipher block chaining CBC, another one is cipher feedback where it is CFB, output feedback OFB, counter, that is CTR. Now, we are going to discuss one by one how the process is going to be happening and what are its merits where you can come out of using this particular mode of operation. So, that is what it is mentioning, electronic codebook, cipher block chaining, cipher feedback, output feedback and counter feedback. Some of the terminology where it is used with respect to these operations are given here, that is initialization vector and initial vector, we usually use it for randomness of the particular encryption process. So, each and every operation with respect to the input and the key, apart from that there will be some initial value to be randomizing the encryption. That process is initiated with the value, that is initial vector. A block of bit to randomize the encryption process, hence produce distinct ciphertext. That is very important, because even an attacker, if he gather the particular ciphertext, he may not be able to match and able to get back the plain text, and also some kind of mapping they cannot be able to do with the, if there is no initialization vector. If there is no initialization vector, then easily they can able to map with one ciphertext and another ciphertext, they may be able to get back the original message. So, initial vector where it is going to be taking care of randomizing the encryption process. For example, if I take he can be one place, it will be encrypted in different ciphertext, other place will be different. So, if I take a word he, then it is very difficult for me to map one he with another key if it is going to be a ciphertext data. Next, nonce. The nonce is number used once, So, nonce is random of pseudo random number to ensure the past communication cannot be reused in replay attack. So, this plays very important role in the case of your replay attack. Suppose some person may gather the information and they may store that information, and later on they can able to act like that other person. To avoid that, there is one term which is going to be used in the case of our mode of operation is nonce. The last one is padding. Padding is if the final block may require padding to fit the block. For example, each and every time I want to break the message into block of 64 bit, whereas the last part of the message cannot be always be a 64 bit. So, during that time I need to add some random bits. That process is called padding. When I am adding that as a last bits, it is called as a padding. So, these are the terminology where you are going to use in the case of your mode of operation: initialization vector or initial vector, nonce and padding. Now, we go to see one by one the modes of operation. The first one is electronic codebook. So, ECB. So, ECB is messages broken into independent block which are encrypted. So, I am going to take each and every message and it is going to be an independent block, and each block is a value which is substituted like a code book. So, hence it is called as an electronic code book. So, now we are taking each block and we are going to which is substituted. So, each block is encoded independently of the other block. That is also a drawback for this particular type of operation, where each block is encoded independently. For example, I am taking a message of P of I. P of I is not going to use, it depends on the P of j. So, Pi is not depending on the Pj. That way, if I take each and every block is going to be done independently. This used in the case of your secure transmission of single values. So, now we can able to understand with respect to this diagram, it shows that how this scheme is working. For encryption, it is C, that is ciphertext, is equal to EK, that is your encryption with a K key. This is a PI, which is the plain text. The decryption, the process is PI is equal to, that is inverse of your encryption, DK of CI. Now, we are going to represent this block to say encryption process, and this block is a decryption process. Now, what I am going to take here is, we can able to see that if I am having a message of size n, then there will be different blocks of input P1, P2, P3, like that I have different block of input, and each of size is n bit. For example, if it is a DES algorithm, it is 64 bit, whereas some other algorithm, whereas the AES algorithm, it will be 128 bit. So, like that you can able to understand this n bit represent 164 bit block. Similarly, this is another 64 bit block. Like that I have n number of 64 bit block. Each and every n bit block is entering into the encryption process, and we can able to observe here only our plain text is varies, whereas the key is going to be the same. This is what we say in the case of your modes of operation. So, where I have a secret key, we can use any algorithm. For example, we already know about this the case of your DES algorithm. If I consider here, this will be 64 bit, the key is 56 bit key. Now, this encryption will be independent of the next. For example, I take P2, P2 is independently encrypted, P3 is independently encrypted, each and every time is going to be independently encrypted. Similarly, you can able to observe in the case of your decryption process. Again, it is going to be taking n bit as a ciphertext and decrypting the opposite direction, where each and every block is taking the K. As you can able to see that all the K are same, that is they are using the same key for all the blocks of the operation. So, what is the remarks on ECB, that is strength, it is simple, right, where it is going to be done independently. It is very simple, as you know the any algorithm, that is you can able to apply that. Weakness, the repetitive information contained in plain text may show it in the plain text, so ciphertext. The repetitive information contained in the plain text may show in the ciphertext if aligned with the block. Then where I can able to observe some of the ciphertext are similar to that of other ciphertext. If same message is encrypted with the same key and sent twice, their ciphertext is same. This the what we want to introduce as the nonce. So, or your initialization vector, sorry, we can use the initialization vector, but here it is not using the initial vector, where here if I am using the same message is encrypted with the same key twice, then the ciphertext are going to be the same. So, these are the weakness of your ECB. So, the application here is where we can use this ECB is if I want to send a short piece of information and also some kind of temporary encryption key, during that time I can go for the ECB. Next comes your cyber blockchaining, that is overcoming the deficiency of ECB. What is the deficiency? As the deficiency we say here, when I am having information, that information contained plain text may show in the ciphertext, it should be aligned in independent box. Another thing is it is same message is encrypted and sent twice, the ciphertext are also going to be the same. So, the repeated same plain text block result different ciphertext, that is what the deficiency where in the case of your ECB. So, each previous cipher block is changed to the input of the current plain text block, hence it is named. So, each and every time when I take a first block and the second block is depending on the input of the first block. So, in addition to that we have initial vector. So, to start a process, earlier process it is using CA is equal to KE, EK of PI, but instead of directly going for CI, we have CO, that is C0, that is your initial value. C0 is equal to IV, IV is nothing but the initial vector. We know very well about this initial vector, where the aim of this initial vector to give the randomness in the case of our encryption process. So, the previous mode of operation is entirely changed with respect to overcome the deficiency of the previous model, that is your ECB. Now, what is addition here is we are taking the initialization vector, and another point here is each and every time the next block is depending on the previous block, the current block is depending on the previous block. So, the use of this is where you can go for bulk data encryption as well as the authentication process. CFB scheme, where we already had this diagram is similar to that of your ECB, but one change here we can able to observe here is, sorry, two changes. One is for the first block there will be an IV initial vector, whereas the second block we can able to see that always it is taking the input from the output of our previous block. So, the encryption process C0 is equal to initial vector, Ci is apart from your EKPI, it is also taking the previous Ci minus 1, that is previous values ciphertext as a one component of your input for the next block. The same process is repeated, that is reversed in the case of your decryption, where in the decryption process where I can take C1 where it is going to be generating, where I record a initial vector, that is C0 is equal to IV. This is given to the next block's input for the decryption process. Okay, as we can able to see that here after the encryption that block is given as the input for the next block, but here before the decryption this block is given as the input output for the particular decryption process. After the decryption it is XORed and it is getting back the plain text. So, we can able to see that the flow is like this, it is flowing from this direction to this direction, where it is able to generalize that encryption process is inverse of your decryption process. So, initial vector which is going to be used. What are the remarks on this CBCS? Yes, the encryption of the block depends on the current and all the blocks of previous. So, hence it is going to be very slow process, because I need to wait until the previous encryption process get over, then only I can go for the next encryption block. And so, repeated plain text blocks are encrypted differently. That is another added advantage with respect to our CBC. So, repeated plain block, earlier case repeated plain blocks are going to be same, but here it is different. Then initialization vector, that is may be sent encrypted in the ECB mode before the rest of the ciphertext. Next mode of operation we have Cipher FeedBack. Cipher FeedBack CFB, here it is going to be same of your CBC, but it need to have some modification. We will see that what is the modification is going to be happening. Here also it is using the same like that of your earlier model CBC. Initial vector is going to be used to start the process, and encrypted previous ciphertext, then combined with the plain text using the XOR operation to produce the current ciphertext. Cipher is feedback to concat with the rest of your IV. So, we can able to see from this particular diagram where it is mentioning initial vector, then encryption process, then we are generating the ciphertext, then R bit of plain text. Now, we can able to observe here feedback chaining, where there is PI, that is your plain text is going to be given in the encryption process, initialization vector is going to be there in the encryption process. So, PI that is C is equal to PI XOR of selected left R, encryption key with the left shift left R, then SI minus 1 or CI minus 1. So, here SI, that is previous SI, that is from S2. If you want to generate S2, that is the next block, I want to generate S2 of next block. When I want to generate C2, for example, I want to generate C2, that is your ciphertext of C2, what I required is P2 into the encryption key, and it is taking the S1 and part of your C1, orbits of your C1, then it is left shifted. This is what you are going to get as the new. This is taking the feedback. It is not taking the entire ciphertext as the previous, it is getting the feedback. So, this is the encryption and decryption process, where it is taking a part of your feedback as the input for the next process. Then here the CB Cipher FeedBack, where it is used as a stream cipher, because if I am taking block cipher, it is going to be slow down the particular process. Each and every time I am going to consider the plain text. In addition to that, I am not taking the plain text into the encryption process. Instead of that, I am taking the initialization vector and also part of my R bits from the cipher blocks I am feeding into the input for my encryption process. So, this mode of operation is suitable for the stream cipher, where I can take a single bit encryption, bit by bit encryption, that is what stream cipher. Block cipher means I take a group of bit, stream cipher will take one bit at a time for the encryption process. In CFB, that is our Cipher FeedBack mode, encipherment decipherment uses the encryption process for underlying block. So, this is what we discussed, the key generator, where it is going to be generating the previous CI value, that is from the previous block, and the SI value where it is going to be given as an encryption, and it is going to be shifted and is given as a R2. Remark on CFB is the block cipher is used as the stream cipher. Now, as what here block cipher, we are not using the block cipher as it is, as I mentioned. Stream cipher means we are going to take single bit or some series of bit for the encryption, stream of bit for the encryption. So, the block cipher is used as a stream cipher. To enable to encrypt any number of bit, example single bit to single character, that is bytes. So, s is equal to 1 is a 1 bit, s is equal to 8, then it is called stream character stream cipher, that means it taking the 8 bit. The ciphertext segment depends on the current and all the preceding plain text segments. The problem here is an corrupted ciphertext segment during the transmission will affect the current and the next several plain text segment. So, that is a very important drawback where you can able to get if there is a transmission or there is any particular bit is corrupted during the encryption, before the encryption process, this corrupted ciphertext segment during the transmission will affect the current and several plain text, because as you see that the decryption is going to be happening on the other side, where it is purely depends upon the previous bits. So, the drawback here is when there is a corrupted bit, definitely it is going to affect the entire message. Next comes the model is output feedback. It is very similar to that of your last Cipher feedback, but output of encryption function, but the change here is the output of encryption function. This is going to be fed as the input, that is your for the encryption process. So, see output is earlier we are taken only the part of your input. So, output of your encryption function, the output of encryption function, output of cipher is feedback, and instead of where it is taking the cipher text. Previous case it takes the cipher text, now we are taking the encrypted function output of your cipher in the feedback instead of cipher text. Feedback is independent of the message, that means the relation between plain text and the cipher text. Ci is equal to Pi XOR of Oi, that means output of the particular, then it is going to be encrypted Oi minus 1, that output is equal to, that is this is what the initial vector is going to be used. So, initial vector 64 bit is encrypted with a key, then the instead of ciphertext we are going to get the feedback, that is what you are mentioned. Instead of ciphertext we are taking the cipher in the is a feedback. Next comes your OFB output feedback scheme, where it is taking this initial vector key and it is taking the particular instead of taking the from the output from the C1, it is taking before the C1, that is what the change over the earlier mode of operation. So, remarks on output feedback is each bit in the ciphertext is independent of previous bit or the bits. You will avoid the propagation error which happens due to the CB cipher feedback chaining. So, it is a pre-computed forward cipher is possible. Security issues, when jth plain text is known, then jth output forwarding cipher will be known, that is one security issue. So, hence requires that IV is a nonce, that means to avoid the replay attack. In the case of your, we avoided overcome the error propagation, but it is going to be having a security issue. So, it will be overcome with the help of your nonce. The last model, that mode of operation is counter, CTR, the encrypted counter value with a key rather than the feedback. So, we are not going to use any previous blocks ciphertext or plain text, simply we are going to introduce the counter value. The counter of each plain will be different, can be any function which produces a sequence which is guaranteed not to reproduce a long time. The relationship it is given Ci is equal to Pi XOR of Oi. So, Oi is where it is taking Ek of I, where it is mainly used in the case of your high speed network encryption, where I want to send more data in a higher data rate, then that kind of applications we use the counter mode of operation. So, this scheme is going to be taking IV initial vector k and n bit, this n bit is going to be XOR with the that is going to be generating a ciphertext. Similarly, it is going to be each and every time we can able to see that there is a counter, instead of taking the feedback from the previous model, it is using the counter. This counter will help you to generate a new ciphertext block from the previous one. This is the process during the encryption, this is the process during the decryption. We can able to observe there will be a counter plus 1 up to counter n minus 1, similarly counter 1, counter 2, counter n in the case of your encryption and the decryption process. So, remarks here is strength needs only the encryption algorithm, random access to the encrypted data, blocks can be processed in parallel, that is why it is fast and fast encryption and decryption. Counter must be known, it must be unknown and unpredictable. That means nobody should be able to guess the counter, then otherwise the system is compromised. Pseudo randomness is the key stream, is the goal. That is very important parameter where you are going to use. So, we are coming to the conclusion, says that we have discussed about the overview of each mode of operation, and also we have discussed about electronic codebook and CBC, CFB, OFB and CTR, the nodes and the remark on each node. Then we also discussed various modes of operation and their merits and the demerits. Thank you.